and welcome to CMP 313, Risk Calculations using HPC and Spot Instances with Morgan Stanley. Today, I am joined by Vikas Chawla, Executive Director, and Emery Azar, Vice President for Morgan Stanley. Vikas is an Executive Director and the lead AWS Technical Architect at Morgan Stanley. Vikas has over 20 years' experience in building out scalable enterprise IT infrastructure systems. He has extensive experience in architecting large-scale HPC workloads and big data systems. Emery is a Vice President at Morgan Stanley and HPC Product Manager. Emery is responsible for the FinOps function for the HPC cloud grid applications, both on-premise and on cloud. Emery has an extensive background across the financial services industry, managing infrastructure estate for regulatory reporting and group finance platforms, application development, and infrastructure architecture. Today, we'll be talking about the evolution of Morgan Stanley's HPC grid workloads on the AWS cloud. I'll kick us off with a brief introduction to the HPC and compute on AWS. Then Vikas will take you through fundamentals of HPC for financial workloads, Morgan Stanley's business drivers for bringing their HPC grid workloads to AWS, and the data storage options they've considered along the way. Finally, Emery will wrap the session with Morgan Stanley's key learnings for their operations, resiliency, and cost optimization needs. I'm going to start off by offering a quick recap of HPC and compute on the Amazon Web Services platform. High-performance computing encompasses a wide number of use cases, including risk calculation, genomics, and research computing. These require significant compute resources. As such, HPC applications and workloads that have been constrained by infrastructure capacity limit insights and innovation. This could be solved for if infrastructure and compute capacity could be increased simply on demand. Among the factors that contribute to our customers' constraints on innovation include high initial CapEx outlays, oversubscription of the capacity, and the constant need for tech refresh. AWS helps to alleviate such concerns by taking care of the undifferentiated heavy lifting of the infrastructure management, providing access to scalable infrastructure, access to latest technologies, and flexible options. This allows for scale and agility not previously practical. The choice of compute offerings and scale we can achieve with our instances has a meaningful impact on alleviating these constraints for our customers. For HPC, we're helping our customers realize that innovation with our instance options, such as our compute-optimized family of instances and our GPU-enabled accelerated computing instances. We've invested in new capabilities, such as faster processors working with Intel and AMD. We've developed our own ARM-based CPU in Graviton. We've also introduced enhanced networking and elastic fabric adapter to remove network bottlenecks. We've added storage options, such as S3, EFS, and FSX for Lustre, to accelerate our customers' data storage needs in the high-performance computing space. All of these have had a profound impact on the performance and scale our customers can achieve. Just as important is working backwards from our customers' need for cost optimization and providing pricing paradigms that fit their needs. Customers can pay for compute capacity by the second with no long-term commitments with on-demand instances. Additionally, customers can make commitments and save up to 72% off of their on-demand with savings plans and reserved instances. Finally, Amazon EC2 Spot allows you to take advantage of unused EC2 capacity in the AWS cloud. Spot instances are available at up to a 90% discount compared to on-demand prices. This was the key option for Morgan Stanley's success, moving their HPC grid workloads to AWS. So we're going to dig a bit deeper on Spot to provide some more background. EC2 Spot is the same instance you leverage today for on-demand and RIs. As I noted, Spot instances are available for up to a 90% discount compared to on-demand prices. Spot instances can be used for various stateless, fault-tolerant, or flexible applications such as big data, containerized workloads, web services, test dev, and as you'll discover today, high-performance computing as well. The key trade-off for leveraging spot instances is that they can be interrupted when another customer requires on-demand instances. And the capacity of any given instance type is low. So the availability of spot instances can vary depending on how many unused EC2 instances that are available. Since it is always possible your spot instance might be interrupted, you must ensure that your application can tolerate spot instance interruptions. You also can adopt different strategies to minimize these interruptions. One key strategy for doing so is instance diversification. By diversifying instance types, you can minimize the possibility that one of your instances might be interrupted. So as I noted, flexibility is key to successful spot adoption. Being able to leverage multiple instance types or instance diversification reduces that chance you'll be interrupted. Also, the capacity optimized strategy for EC2 autoscaling and Spot Fleet provisions spot instances from the most available instance pools by analyzing capacity metrics. The Spot Instance Advisor helps you determine what the least chance of interruption that you will have on particular spot instances is and provides savings that you would get over those on-demand rates. Another strategy is being time flexible. If you have workloads that are not time sensitive, like batch jobs with no SLA or machine learning training jobs, but you require some specific instance types, using less capacity over a longer period of time can be an effective approach. Finally, if you have specific instance requirements, you can reduce the potential of interruptions with Spot by leveraging instance capacity across multiple regions. Flexibility is indeed key to allow you to access the most spot capacity and minimize interruptions. Some features we've added to Spot Fleets help us to determine what is the best strategy based on what your business needs are for leveraging Spot. So if your fleet is small or runs for a short period of time, the probability that your spot instance might be interrupted is rather low, even with the instances in a single spot capacity pool. Therefore, lowest price is a strategy that is likely to meet your needs while providing the lowest cost, as the spot instances will come from the pool with the lowest price. This is a default strategy. With a diversified strategy, the spot instances requested are distributed from across all capacity pools that you specify. Using this strategy makes your fleet less sensitive to increases in the spot price in any one pool over a given time. It also helps you minimize operational risk if that is your primary driver. Finally, if your fleet request runs workloads that might have a higher cost of interruption, and that interruption is associated with the restart of work, such as in high-performance computing, then the capacity optimized strategy is the most ideal. This strategy offers the possibility of few interruptions, which can lower the overall cost of your workload. With spot instances, pricing changes slowly over time based over long-term trends in supply and demand, but the capacity does fluctuate in real time. So the capacity optimized strategy will automatically launch spot instances in the most available pools by looking at the real-time capacity data and predicting which are the most available. This allocation strategy has been a key factor in Morgan Stanley's success with their HPC grid workloads. With that, I will hand it over to Vikas, who's going to share some of the business drivers that influenced their decision to bring their HPC grid workloads to the AWS cloud. Vikas?
Thank you, Anthony. So I'd like to start off with providing some business rationale for Morgan Stanley's decision to migrate the HPC workload to Amazon. So Morgan Stanley, as you know, is a very large international financial institution, one of the largest in the world. And we have to calculate risk for regulatory reasons across varieties of our business, whether it's credit risk, market risk, counterparty risk, equity risk. And we have to do this valuation of risk to find out our exposure, as well as to manage our P&L. Now, when we have to value our risk, so let's take the equity risk portfolio. So we have to do the valuation not just for point in time, but we have to model market conditions and different indices moving in either direction by several percentage points. So if you remember, mid last year, we had large fluctuation in the equities market with indexes shifting 4, 6, 8, sometimes 12 percentage points in a single day. So we have to do the valuation of our entire portfolio through all these scenarios, as well as combinations that can impact the market, like the yield curve, dividend curve, so on and so forth. So set a framework of the number of computation we need to do. We have a few million equities positions. We have to run through at least one trading year, which is 250 days, and we have to do a few thousand scenarios. So a combination of that leads to about 3 billion data points on a nightly basis. And periodically, we have to do a 3-year run, which is about 9 billion data points that we have to calculate. In essence, this is what is called value at risk, and these are extremely compute intensive. Then the workload is variable. We trade in markets, we trade in products, products expire, and it's very difficult to predict the amount of workload. Then comes the start and finish time. So by the time that this end of day risk calculation has to finish, and its downstream dependencies, it definitely has to finish much before the start of the trading day. The start time can vary because it relies on multiple manual processes, as well as the traders have to sign off on the books. So that can vary. Now, on a good day, we might have 6 hours. On a day which has a lot of volatility, we might have just 3 hours. And this is where the cloud is really attractive. On a good day, we can use 50,000 cores. On a day we have just half the time, we can use 100,000 cores, assuming that we have eliminated all the other bottlenecks, which we have. So this way we pay the same amount of money, but can deliver that stringent SLA to the business with the elasticity of the cloud. The other thing to note is that our current risk models are based on the market conditions that have happened so far. Tomorrow or day after, there might be a black swan, purple swan, red swan. We don't know, some event that necessitates the creation of more complex algorithms which are more compute intensive. Also, our industry is being subjected to constant regulation, which is more regulation is being imposed on us. And every time a new regulation necessitates the calculation of more risk, and other requires more compute. And finally, a lot of time the business will come to us saying that they think they have an opportunity either to make money, save money, or reduce risk. And that requires maybe a lot of more additional compute capacity. In the past, we would have to build that out, and keep in mind, it might be experimental. They are just playing with it. What the cloud gives the business users the ability to spin up more compute and test their scenarios that they think would help them either make money or save money. Also, we can tie a business value, a dollar value, to the work that they want to do. So they know if they use this algorithm and it costs them X dollars, that helps them easily quantify very quickly rather than having to wait for an on-prem rack and stack. The other thing to note is that on-prem, we have a limited capacity. So a lot of the business processes are making sure that capacity is used to the fullest. So a lot of the processes that can be done in parallel are done serially just to make good use of that business, of that compute footprint. In the cloud, no such limitation exists. Whatever we can do in parallel, we can spin up compute, and only limited by the imagination of the app dev team and the capacity that Amazon can provide, and it has got pretty deep pools. So the elasticity of the cloud presents a very attractive feature, especially for calculating risk for a bank like Morgan Stanley. Now, I wanted to cover some fundamentals of HPC. Now, whether HPC is used in financial risk or oil and natural gas, doesn't matter. The fundamentals remain the same. What HPC requires is fast compute. It requires high throughput networks. It requires access to low latency storage. And finally, it requires a grid broker. So grid broker is like the brains. It gets a job, breaks it up into small tasks, submits these small tasks to the compute, and then checks the status. If the task is not finished or a compute has failed, then it retransmits the tasks and then finds the best placement of the task based on the compute available, and then finally collects the accounting records. So the grid scheduler is the element that is responsible for orchestration of compute. Finally, you need multi-layered caching, because finally the compute is acting on data. One of the guiding principles we use is that the compute needs to be kept busy 90 to 95% of the time. So that's what we strive to do with moving the data as close to the compute as possible. Now I wanted to go over some of the guiding principles that we have used to migrate a bunch of HPC applications to the cloud. So the first thing is, when we started our journey, we went with this thing in mind that we have to refactor the applications. It cannot be a lift and shift, which means that the application needs to be in a Docker container, needs to read from object storage like S3, and any native storage that the cloud provides and is used in that architecture. From the infrastructure perspective, we decided to use all cloud native technology, whether it is for monitoring, alerting, logging, or security assurance. Everything would be cloud native to minimize technical debt. Finally, all the infrastructure instantiation we are doing, whether it is landing zone, IAM, S3, EFS, guardrails, everything would be infrastructure as code. And we at Morgan Stanley are big users of Terraform. The main focus is security. Because we are a bank, highly regulated industry, the last thing we want to do is be on the cover of the Wall Street Journal for the wrong reason. When we hire from outside the financial industry, one feedback I constantly get is the amount of security that we have implemented in Amazon, and the defense in depth we have implemented is far more than what they are used to. So the security bar is high, the principle of least privilege, we do our best to adhere to that, but that helps us to keep the environment really locked down. Scalability. So just to give you an example, the first workload that we had migrated was scaling to 25,000 cores at the beginning. That was the requirement. Now they are scaling to over 200,000 cores, that is 8x that, without us having to change architecture. The only thing we have done is gone and increased the subnet size to accommodate more compute. The last thing is reliability. We have hard SLAs. We are monitored by internal and external regulators. So reliability is paramount for all the deployments. Then is the blueprint. Because we have many risk workloads, we created a blueprint. And using that blueprint, we have onboarded many applications, and we continue to refine the blueprint. The other thing is we have used Spot. So all our compute is using EC2 Spot, and Emre, my colleague, is going to talk about it. Hygiene. So what we do is we recreate the entire environment once a week. We tear it down on Saturday, bring it back up on Sunday, and that ensures hygiene and repeatability, and of course helps us save some costs. Then SDLC. We have multiple environments, dev, UAT, prod. We ensure that everything is deployed in that order to ensure that there are no bugs introduced, and we do adequate testing before deployment. Agile iterative strategies, deploy small changes, deploy fast changes. And just to give an example, or just from my own experience, halfway through the cloud journey, Morgan Stanley was keen on adapting the agile principles, and we had to get all schooled into the agile principles. And initially I was complaining about it. It was a stretch, to wrap my head around all the ceremonies. But now that it's been over a year and a half that we have been using it, I think the discipline that Agile imposes on us, or Agile ceremonies, has definitely helped speed up our deployment. So now I'm a big fan of Agile. Finally, it's a principle that I hold very dear to my heart, that stability trumps agility. Introduce small changes, test them well, because stability is paramount. We can sacrifice the speed, but ensuring the stability of the application. Now I wanted to walk you through the overarching architecture, or the blueprint, that we have used for our applications. On the left-hand side, you see our on-prem data centers. That's where we fire up the infrastructure orchestrator, which instantiates compute in Amazon via Terraform. We are using a middleware called IBM Spectrum Symphony. The Symphony clients submit on-prem, submit the workload. That workload via a series of load balancers, both on-prem and on Amazon, contact the Symphony manager, the master, and SSM, and they in turn instantiate compute. So we use something called Spot Fleet Request to instantiate our Spot instances, and that has a manifest, and the manifest has a variety of things, including the configuration that we need for customizing a node. And that is the kernel settings, a lot of the things that Symphony needs. Also, it has the subnets, which defines the AZs, and the variety of instance types that we use, and Emre, my colleague, is going to talk a little bit about it. The Symphony has another component called the host factory, which spins up and down the compute based on the workload and the pressure coming in. So it increases the number of compute or tears it down as the pressure decreases. Now, when a compute node is spun up, the first thing it does is pulls down a Docker image of the Symphony client. The Symphony client contacts the Symphony master and SSM and says, hey, I'm ready for compute. And then a Docker image is pulled down, which has the client code for calculation. And then it runs the calculation. It reads the data from either FSX for Lustre or EFS. And then after the calculation is done, it sends the data either back via Symphony or writes the results back to FSX for Lustre or EFS, depending on the use case and the amount of data that needs to be written back. So this is architecture in a nutshell. Of course, we have multiple regions, multiple direct connect circuits for full redundancy. We also have HA for the Symphony master, and there's a backup master, and it shares the state via EFS. Now, there's a lot of intricacies hidden behind this architecture. We can talk a lot about security because we have full security of encryption of data at rest and in motion, north, south, and east, west. We also can talk a lot about logging because we have applications that log 100 gigs a day versus applications that log more than 5 terabytes an hour. So where we have used a variety of logging patterns. But today we thought that let's talk about storage because we think that that's also a subject that will be of interest to all of you. So if you look at the components of storage used in the previous slide, we are using 3 storage components. We have Amazon S3, we have EFS, and FSX for Lustre. When we started our journey, at that time EFS was not approved because it did not support encryption of data in motion and data at rest using CMK. So we started storing the model files that are used for calculation on S3. Now, there's a large amount of reads going on for this. And so just to give an example, the one run results in about 100 million reads. And there are 3 runs based on the various regions. So we have over 300 million reads, and that results in a large number of KMS lookups. So basically each read from KMS or S3 would also result in a lookup from KMS. Initially, when we are scaling up, everything was fine. But one day I get a call from our application owner, and says, Vikas, can you help me decipher the bill? And when I looked at the bill, I fell off the chair because the cost of EC2 was 10 grand and the cost of KMS was $15,000. And that was just like, that gave me an answer that was staring at my face is S3 is the wrong architecture for this application. So then we switched over to EFS. Luckily, by that time, EFS supported encryption of data at rest with CMK as well as encryption in motion with the EFS mount helper. And then we just allocated the maxed I/O mode, which gave us the throughput we need. And from that time, the performance is much better and the costs are also uniform and stable. After that, S3 has introduced the bucket level encryption, bucket level keys, that is. So every lookup, every object lookup will not result in a KMS lookup. But even then, we have done benchmarks and we see that the cost of the performance of EFS is much better than what we get with S3, even with bucket level keys. So we have continued using EFS for performance reasons. Now, just to compare and contrast EFS and Lustre, right? To me, Lustre is EFS on steroids because both Lustre and EFS support POSIX semantics. So if your application is doing millions of IOPS or tens of gigabytes per second of read-write, then definitely use Lustre, right? But to about 500,000 of IOPS, I think EFS is a fine solution. But if you use Lustre, I think you have to be wary of, or use the word wary, but at least be cognizant of two major differences between Lustre and EFS. Now, those two differences are, the first thing is, when you allocate EFS, you have a choice of either zonal allocation, that means putting the endpoint in one zone, or a regional allocation, that means dropping the endpoint across multiple AZs. In Lustre, you have no such option. When you create Lustre, you have to choose a particular AZ and the endpoint is created only in that AZ. Which means that if you are positioning compute or deploying compute in any other AZ, you have to pay charges for cross-AZ traffic. The second thing is that EFS, as we talked about, provides encryption through the mount helper. For Lustre, there is no such thing. The only way you can get encryption is via instance types that support VPC encryption. That are the new Ice Lake, the M6Is, you have R5Ns or I3EN, but a very limited number of instances support VPC encryption, which means that if you're using Spot, and you are limited to that pool, and you have to put adequate attention on whether you are able to get Spot instances from that pool or not. So in our case, to accommodate for that, we have firstly to allow for limiting to the instance types. We have put service control policies to limit the account to only spin up only those instance types, and then the choice of Spot instances is definitely something that we have been working through. Now comes the EFS performance modes, right? So as I talked about the high workload, the high ops that we need, and I have a graph showing the amount of IOPS we are doing. We have chosen max IO because of the 500,000 IOPS or close to that we are doing. We are doing over 300,000. And initially, when we did the Symphony master and secondary backup solution, because it also required a shared file system, we went with max IO because they're already using it. And we realized the latency was killing us for that particular use case. So when we switched to general purpose, it worked just fine. And I'm assuming that general purpose, based on the name, would work for majority of the workloads. But of course, if your workload requires a large number of IOPS, which is more than 35,000, because general purpose caps off at 35,000, you have to use max IO, but then you have to deal with the higher latency and the metadata, higher latency for file read-write, as well as metadata lookup for max IO. So there's a trade-off that we have to be aware of. So this is our workload, high IOPS, small files, about thousands of files. So it's over 65,000 files. Average size is about 88 kilobyte per file, and large number of reads. So we are doing about peaking at about 300,000 IOPS from about 2,000 clients. And again, each client has multiple Docker containers. So basically about 20 to 30,000 containers are doing the IOPS. As I said, read about 300, resulting in over 300 million file reads on a daily basis, right? So a significant amount of high IOPS small file. So if you have that workload, then this architecture works really well. It works well for us. So just to recap the EFS recommendations for the HPC, this particular workload, we use max.io. For the IOPS, we use provision throughput because if you use burstable, the other option will be burstable. You will not get a steady state. Ours is a steady state throughput that we need, and that's why we are going with provisioned IOPS. Then we have encryption of rest with CMK. We have caching at the client level. We use a product called EHCache, which caches the files to prevent multiple reopens. We have used the latest version of OS. I would say definitely RHEL 7.3 and higher, preferably RHEL 8. The default mount options, and that's what Amazon recommends. And directory structure. Again, I think this is a recommendation from Amazon also that's proven by our experience. That keep the files less than 10,000 in a directory. You can have the nested directory structure. We break it down by time and hour and things like that. You can have a nested structure based on the first letter of the file name. People have a variety of schemes, but as long as your directory structure is balanced, you will get a good throughput. This is an architecture which talks about locality, which is essential for FSX, mainly for FSX, but also relevant for EFS. If you see in this diagram, you have FSX and EFS in one AZ. The compute is pulling data, is spread across multiple AZs, and we are pulling pulling data across AZs. The second diagram has locality, where FSX and EFS are local to the compute in that AZ. Now, just to give the importance of this, we are doing a POC with Lustre, and what we found on a day that the Lustre charges were about $800, $850, while the cross AZ charges was $1,500. So nearly 2x the cost of Lustre because of the amount of data we are pulling in. So thereby, you have to either figure out instantiate compute only in the place where Lustre has the endpoint, or have multiple Lustre file systems and sync data across them. And that is applicable for EFS also, because EFS has regional allocation, ensuring that when you mount the EFS file system, you're accessing the mount point that is local to the AZ to minimize cross-AZ data transfer for performance and cost. Now I'm going to hand it over to my colleague Emre, who's going to talk about operations and resilience and solid DevOps practices that we have used and has held us in good stead. So thank you.
Thank you, Vikas. Let's now talk about some of the challenges we faced, lessons we've learned with regards to the operational elements of this approach, and how we achieved resilience. Observability is key to understanding and troubleshooting our configuration. We regularly leverage the EC2 dashboard or CLI tools to check a few metrics. How quickly are we scaling up instances? Which instance families and sizes are we getting? Which availability zone are they in? Do they match what we've configured and asked for? We also use storage-related dashboards to check read-write throughput, IOPS, metadata operations to see if there are any bottlenecks or behaviors we did not expect. We have defined CloudWatch alerts and dashboards to monitor instance evictions or spot interruptions. We aim to employ best-class DevOps practices and tools. We use a modern CI/CD pipeline and tools like PagerDuty for alerting and customer escalations. All our engineers are SREs and are on call on a rotation basis to ensure that they feel the pain in case the product they have built is causing issues to our customers. We pay close attention to the alignment of our compute instances and storage services within and across availability zones. We consider potential latency impact when we traverse AZs and the associated data transfer costs. We also monitor the number of cores we're using. Are we using them efficiently? What's our CPU utilization profile? Are we making use of the entire core? Increasing compute core count may not be a viable solution if the bottleneck is elsewhere. Or worse, we might make the bottleneck worse by increasing our core count, resulting from more API calls and connections to other services. We maintain our awareness on this. When we set up our multi-region strategy for resiliency and failovers, we took a very close look at how our application behaves when our on-premise connections are traversing the network to reach a region that has high latency. For example, we're starting somewhere in the US East Coast and connecting to AWS US West 2. We have benefited from TCP tuning using a multi-stream setup. With our use of IBM Spectrum Symphony, our workload distribution and automation tool, we defined our configurations to be aware of the limitations on how many instances we can efficiently run in each cluster. We considered regional dimensions for applications we have onboarded, for example, end-of-day batches for each time zone, and we've created multiple clusters to manage them separately to improve efficiency. Now let's talk about some of the EC2 Spot instance best practices. As Vikas stated before, use of Spot instances was key to our financial viability for using AWS EC2. With Spot, AWS issues a 2-minute warning that the instance will be reclaimed. We've developed our applications to gracefully handle Spot interruption notices. When we receive these notices, we stop scheduling any more tasks on that instance. We've also looked at what we want to do with active tasks on that instance. Do we abort them and restart on another instance? Or do we let them run to completion within the 2-minute warning window? For some of our use cases, most tasks complete in seconds. And if they don't complete within the notice window, we've leveraged the feature set in IBM Spectrum Symphony for automatic resubmission of that task on another instance. We also start up instances in multiple availability zones within the same region. This provides resilience for our applications in case there's a service outage in one availability zone, and more importantly, allows us to optimize our Spot request fulfillment. We leverage a wide variety of instance types and sizes that suit our application profiles. This helps us cast a wider net, get the instances and core count we need, optimizing our resilience and minimizing Spot interruption rates. Initially, when we configured our Spot fleet requests with the cost-optimized strategy, our interruption rates were consistently over 15%. We worked with our AWS account team and changed our allocation strategy to capacity optimized, which meant that we get instance families and sizes that have a lower likelihood of getting reclaimed via Spot interruptions. As I've just mentioned before, we set our strategy for deploying across multiple regions to improve our resiliency to handle potential service outages or unavailability of EC2 instances in a single region. We've also focused on eliminating single points of failure. We use direct connect links to AWS, and we configured them to be hosted by multiple lines of connections from different networking vendors and from 2 different cloud services hubs on the Morgan Stanley side. For our workload distribution and application tooling, we also leverage active-active or primary backup type configurations to ensure that we eliminate or minimize service interruptions and delays. Our Spot fleet requests have over 20 instance families and sizes defined, leveraging all availability zones in each region, giving us more than 120 instances we can deploy our workloads on. We've leveraged AWS Lambda functions to capture Spot interruptions by region, availability zone, and instance type, which allows us to observe the rate of interruptions and the impact they have on our workloads. We've set a threshold of 10% across all, and we have been able to stay well below that threshold for more than 99% of the time. The graph presented here shows the trend of our Spot interruption rates compared to the 10% threshold we have set, and how we compare against our peers who leverage Spot instances for more than 50,000 cores. This data was provided by our AWS account team. This graph shows our year-to-date Spot interruption rates. When we experienced the spike on May 23rd, we were able to quickly switch to using on-demand instances for a short period to ensure our application stability and workload completion. Let's do a quick summary of the key lessons learned. Scaling up to tens of thousands of cores is no easy feat, especially when you're using Spot instances. We've learned and adapted as we progressed. How do we ensure instance diversity and resilience? Which Spot strategy should we use? Cost optimized or capacity optimized for optimal configuration? Scaling at this level also presents challenges in logging, choice of the right storage platform, and ensuring that we're not saturating the network in any direction. US East 1 is our primary region, and we selected US West 2 as our secondary region based on various factors, with instance pool depth being one of the most important ones. Replicating our configuration for networking, connectivity from Morgan Stanley to AWS, IAM policies, configuring application and middleware, tooling dynamically to switch from one region to another, or execute workload on both concurrently took longer than we anticipated. Security and IAM policies require close attention with the AWS shared responsibility model, and to ensure that we adhere to the minimum privilege principle. We defined policies for application IDs and user IDs and what they are entitled to do. We're big fans of agile principles for application development. Fail fast, adapt, and resolve quickly. Last but not least, we work very closely with our AWS technical account team. They've been a true partner. They've been with us every step of the way. They actively engage with our various use cases and projects, and they play a key role in connecting us with the product managers at AWS to discuss challenges and influence their product roadmap. With AWS, we get deep pools of EC2 compute, storage options, observability dashboards, and many other services we can benefit from. So let's talk about how we optimize our EC2 compute costs. As most of you probably know, AWS offers various EC2 instance options, including reserved, on-demand, and Spot instances. Knowing your application usage pattern plays a key role in determining which option is right for us. Do our application run sustained workloads over extended periods of time? Do we need very large compute capacity? Is it sustained or does it come in bursts? How long does each task run for? Can our application handle Spot interruptions gracefully and with minimal impact to our executions? These are some of the questions we've answered before deciding on which instance type to use. For an application workload pattern which has sustained runs for more than 18 hours a day, 7 days a week, we get the best value from reserved instances with a 1-year or 3-year commitment agreement. This will ensure that our EC2 instances are always up and ready to use, and are not subject to any reclaims or interruptions, while we get discounted pricing compared to on-demand instances. If our application workload runs for a few hours a day, or it comes in bursts with high compute demand, but the potential Spot interruptions would disrupt our individual tasks' completion, which might result in missed SLAs or having to rerun tasks, we get the best value from leveraging on-demand instances. On-demand instances are ours from the moment we commission them until we terminate them. No reclaims, no interruptions. But these are the most expensive instance types from a unit cost perspective. It is absolutely critical to ensure that we terminate these instances once our workload's complete. Otherwise, we'd be racking up charges potentially into the tens of thousands of dollars overnight. There's another flavor of on-demand instances available called on-demand capacity reservations. With this option, we can make a 1-year or 3-year commitment, which gives us a reservation for on-demand instances. The key aspect of this option is that we need to manage the startup and shutdown of these instances based on our application usage patterns. If our workload is expected to start at 9 a.m. each weekday, We plan ahead and start up our instances before the workloads hit. We also remember to shut them down when our workload is completed. This option can become cost-effective if our applications can't handle spot interruptions and we have large periods of no activity, such as weekends or nights, where making a commit to reserved instances is not ideal. Spot instances are the lowest cost option. This option gives us the best price point, but we need to carefully assess and know our application behavior. If our application runs in bursts, scaling up and down multiple times a day, and our tasks are small enough that we can afford to restart them, this is the best option we choose. With spot instances, the likelihood of interruptions increase as you move to the larger and newer instance families, as they are the preferred instances by practically everyone. If you recall the points we made earlier about instance diversification and capacity optimized spot strategy, this is the reason. We want to get as many instances and cores we ask for as quickly as possible with the least likelihood of interruptions. This ensures that our application runs smoothly, tasks finish quickly, and we don't have to carry the cost of compute capacity for periods of no activity. It is also worth noting that we use a mixture of reserved versus on-demand versus spot within each application as well. For example, we use reserved instances for things like CSRV routers, Symphony masters, and session managers, as they need to be up 24/7, and we use spot for all worker nodes. Here's an example. This application scales up to 25,000 cores at 5 a.m. each weekday when their work operations start, and they have sustained workloads requiring those 25,000 cores until 6 p.m. There's no activity overnight or on the weekends. Using pricing data from AWS, we modeled this pattern against reserved, on-demand, and spot instance types. Because of the application's usage pattern, the lack of activity during certain periods, reserved instances would be an expensive option for this workload. While spot instance-based pricing appears like a no-brainer, this application manages interactive risk calculations and pricing submissions from end users. It is very important for this line of business that they get their results as quickly as possible. In other words, we can't afford to wait for instances to be started up as demand increases during the day, or have to rerun tasks because a spot instance was reclaimed. For this application, the best option is to start with pre-configured on-demand instances that are up between 5 a.m. and 6 p.m., ready to receive workload almost instantaneously, and generate results for the end users as quickly as possible. Let's recap some of the key lessons learned from this section. Reserved instances may not be the cost-optimal option depending on how often we're going to have active workloads using them. Choose instance types wisely. We determine what the best option for our application is. We leverage the Cost Explorer, budgets, cost and usage reports to monitor what our cost trends look like. We set up alerts to warn us when our expenditures suddenly go out of reference ranges. We check for services that we use and how much we're paying for them. Do we still need them? Are we capturing logs for eternity that no one looks at? We are very frugal when it comes to what we bring back on premises. Obviously, we want to bring back the results for our calculations, as most of them continue their journey inside our organization. They are input data sets to other applications. We have asked ourselves, do we need to bring back EC2 instance and application logs on-prem? What will we use them for? If it's for troubleshooting, it's probably better to keep them on AWS and manage a retention period. When there's an issue we need to investigate, we can find what we're looking for. Otherwise, if we bring everything back on-prem, we'd be spending a considerable amount of money on data transfer charges with potentially minimal or no value to our organization. Similarly, as we mentioned before, data locality is an important factor as well. That's having our data and EC2 instances in the same availability zone, which can help achieve optimal performance while avoiding cross-AZ costs. Lastly, for a large enterprise scale deployment, we've invested in FinOps resources and tooling. We have insights into where our spend is. It's very common that we identify charges for services that we either no longer need or we can make quick changes to our configuration to reduce these costs. We have also deployed a SaaS product called Cloudability, which ingests costs and usage data from AWS and provides business intelligence and financial reporting for our applications. I'll hand it back to Anthony now for some closing remarks. Thank you.
On behalf of AWS, I'd like to thank Vikas and Imre for sharing Morgan Stanley's journey to AWS Cloud with us. Thank you very much for joining us,